Quickly about me, my name is Loren Stewart. I work at Exida, helping with the mechanical clients. I work as a safety engineer here, and I do the assessments of safety products, the certifications, the audits, and I also am doing research on stiction, mechanical failure rates, and the 2H initiative. A little bit about Exida. We have our knowledge base of our books and training and tools and our experts. We also do life cycle services and assessment and certification services. We have offices all around the world, so wherever you are or wherever your customers are, we are close by. Quickly about what we offer. We at Exida concentrate on everything functional safety, the process, the products, and the people. So we have consulting in alarm management and the IEC 61508, 511, 62061, 26262, and ISA S99. We have our engineering tools, our product certification, our training, our reference material, and our personnel certification. A few key points that we're going to discuss today are the distinction between failure rate prediction and estimation methods, details about the procedures used to obtain generic failure rates for certain mechanical equipment using FMEDA predictions and ARIDA estimation, along with other methods used in industry today. We will talk about specific equipment failure rates compared, and when differences in the results exist between the two methods, plausible explanations for the differences are provided. We are going to look at equipment examples, including representative of topside equipment examples and subsea examples. We have relative merits for each method, and we discuss that along with comparisons to industry database and field studies. We will talk about what is a realistic failure rate for mechanical devices and what do you do if you find yourself looking at unrealistic numbers. Just to give a little general background, we talk about IEC 61508 being the functional safety guideline, and they define functional safety goal as the automatic safety function will perform the intended function correctly, or the system will fail in a predictable or a safe manner. So while we are going through all of the slides today, we're going to keep what functional safety is exactly in our minds. And for a little bit more background, we're going to look at the detailed safety life cycle. And why do you really need realistic failure rate data for mechanical components? What does it really matter? The failure rates from manufacturer safety manuals and failure rate databases directly go into SIF conceptual design, reliability, and safety calculations. So if your failure rate data isn't realistic, your calculations won't be correct. And if your calculations aren't correct, you will think that you're going to achieve a certain SIL level or a risk reduction factor, and you think you might be very safe. But in fact, the reality is if you put unrealistic numbers in, you're not going to achieve realistic results. So some people say that there's no such thing as a realistic failure data, but many others are confident in their failure data. So where does this failure data come from? How do different methods compare? We're going to look at all of this today. There are two fundamental techniques for failure data, for getting failure data. You have the estimation technique and the prediction technique. The estimation is based on estimating your failure rates based on failure data. And the prediction technique is based on test results or design strength analysis. And how do you get these failure data points? We're going to first dig into the estimation. We're going to look at the failure rate techniques. Based on estimation, are broken down into three different methods. You have your manufactured field return data studies, you have your industry databases, and your end user field failure studies. And all of these, like most things in life, have pros and cons that come along with it. So we're going to dive into each of these three techniques of estimation and see where the pros and cons lay. So the manufacturer field return studies. The positive and the pro is that it's real data, and that can be very, very valuable. But you also have to consider that the calculation methods may vary widely from manufacturer to manufacturer. You can't necessarily know what percentage of actual failures are returned, and that's a big deal, and we'll see why later on. And the different definitions of failure per manufacturer to manufacturer. So many manufacturers classify a returned item as a failure only if the manufacturing defect is found. So many return items are marked no problem found or systematic failure or we're not going to worry about it. The calculations are sometimes done where operation hours are estimated based on shipping records, and it's assumed that all failures are returned, and that's extremely optimistic. Depending on the price of your part compared to the system, if it is a low price item, you probably won't even see 50% of your returns. Your customers might think that it's cheaper or easier for them just to throw it away and order a new part instead of sending it back. However, this data can be very valuable to identify root causes and to compare to establish lower bounds on failure rates. Next, we're going to look at industry database. Once again, the positive here is that it is real data. That's so valuable. The cons of industry databases are there's not a lot of data available. Once again, there's different definitions of what a failure is, and the categorizing and merging technologies together because they might not have the information to separate them. And there's a lack of fault isolation. So while we're talking about industry databases, I'm going to bring up AREDA. AREDA is a whole collection of offshore companies in the North Sea. It provides very useful data on the process equipment, and it's kept up to date with the latest publication, which just released early this summer in 2015. AREDA is considered by most people the #1 and the best industry database. It is that has a lot of valuable information in their books. To kind of take a quick look inside of what the AREDA books look like, they provide a total failure rate based on a given population and recorded operating hours. So for this example, we're looking at a pressure transmitter. And it has a population of 32 units. Up in the top left-hand corner, you see 32 population, and 1,122,000 unit operating hours. It states a total mean for the failure rate at the operation time as 420 fits. The next estimation technique is the end user field failure data studies. And these studies have sufficient information represent a rich opportunity to obtain failure rate and failure mode information about a product in a specific application. This is where this differs. The positive, once again, it's real data, and it is involving a specific application. The cons are there's variations of amounts of data collected. Once again, you have a different definition of failure per each end user. They might categorize and merge different technologies, just as the last example we looked at. And once again, there's a lack of fault isolation. So after performing dozens of studies, exida experience recognizes that data collection with the data collection process varies by an order of magnitude or more. You don't know necessarily when a failure report was written, what is their definition of a failure, are there as found conditions recorded during a proof test, what are the operating conditions. These are just a few questions that come up per end user field failure data studies. One of the most important things that we have to look at is random versus systematic failures. And IEC 61508 defines both random and systematic failures. They say that a random failure occurs at a random time, which results from one or more degraded mechanisms. Well, that could be a lot of things. What we concentrate on is a systematic failure. Systematic failures is defined as a failure related in a deterministic way to a certain cause, which can only be eliminated by a modification of the design or of the manufacturing process, operational procedures, documentation, or other relevant factors. So if it fails in the systematic and deterministic way and can be eliminated by a modification of documents or designs, it's systematic. We tend to think if it can't fall into that definition, random failures are everything else. So is there a consistent interpretation between random versus systematic? What exida did was send out a survey to many people we have on our mailing list, asking them to take a quick quiz to see where they thought different situations were random or systematic. And these situations were actual situations we saw in the field. So the first failure we're going to look at is a failure occurred when a de-energized trip remote actuated valve snapped closed and shut down the process during normal operation. The failure was traced to the PLC logic solver rated to 50 degrees Celsius, where an output module failed de-energized. A component in the output module, a transistor, had failed such that it could no longer conduct current. The ambient temperature was quite hot that day. It was 55 degrees Celsius. And an X-ray of the transistor showed a burned out wire, likely due to electrical overstress. So take a moment and think, do you consider this random or systematic? Well, our survey showed that another choice was end-of-life failure. Sorry, I forgot to mention that. As you can see, 57% said random, 39% said systematic. So there is not a strong choice. They don't necessarily know. Many people argue systematic, no, random, no, even end-of-life failure. Another example is a maintenance technician routinely checks and adjusts the trip points on a generator activation relay. The procedures for checking and adjusting the relay were correct. Although a rare event, occasionally a mistake is made with the adjustment. In one case, the trip point was set too low and the power generator did not start as needed and the power system failed. Once again, take a moment to think, is this a random failure or a systematic failure in your mind? Well, as you can see here, most people thought it was a systematic failure at 57%, where almost half, 43%, said random failure. So there's once again a lot of disagreement. Now we're going to go away from the estimation and look at the prediction failure data. So it was decided that something better is needed. Don't get me wrong, all of those estimation failure data are very valuable, but there's something that needs to be more consistent. Failure rate prediction techniques are predicting the failure rates based on test results or design strength analysis. And there's two ways of predicting failure rates. You have your B10 data and your FMEDA data. Once again, just as we did with the estimation, we're going to look further into what the B10 data provides and the FMEDA. Just as the estimation, each has their pros and cons. Let's talk about first what B10 or cycle test failure data actually is. So the B10 method uses cycle test data, and the cycle test is done until 10% of the units fail. And the number of cycles is called the B10 point because of 10%. So the failure rate is calculated by dividing 10% failure count by the time period. And that the failure rate is assumed to be 50% dangerous and 50% safe. And it is assumed that no other failure modes exist. So the B10 method assumes that it's a constant failure rate during the useful life is due entirely to premature wear out, and all other failure modes are completely insignificant. Well, research shows other failure modes become significant when the products do not move frequently, and it's not a dynamic applications. Some failure modes become significant if a product is static or motionless for just 100 hours. That's not a lot of time. Now we're going to look at FMEDA, or failure modes, effect, and diagnostic analysis. So the FMEDA will be performed a study of each component and how that component failure will affect the device. And it will estimate or test how well the automatic diagnostic and proof test will detect component failure. FMEDA's look at the environment that the device is set in. So the component failure rates are a function of the operating environment. Therefore, the FMEDA analysis is done for a defined environment. And as you can see, we have 6 different environmental profiles. We have your cabinet mounted with a climate control, general field mounted, no self-heating, general field mounted with self-heating. You have your subsea, your offshore, and your process wetted. And as you can see, there's a bunch of information about shock, vibration, ambient temperature, seasonal temperature. All of these make a difference in what category the FMEDA analysis is done. So we're going to take a quick look at FMEDA results, and this is what you get at the end of your FMEDA. It shows differences in designs, applications, and operating conditions. So first we're going to take a look, and this is a double port guided valve, and at first it was done in a clean service application. You have failure categories as fail safe, fail dangerous, undetected, and no effect. And it is looked at as on close on trip as a full stroke, close on trip as tight shutoff, and an open on trip application. And the bottom shows you the same failure categories, the same failure rates or the same failure applications, but this time it's done in a severe service application. Now, people sometimes ask, well, how accurate are FMEDAs? Well, the accuracy of the FMEDA, it depends on the accuracy of the component database. Once again, the old saying goes, garbage in, garbage out. So the component database must include failure rates and failure mode distributions of each component as a function of one or more operating profiles. And the useful life of each component must also be listed as a function of operating profile. So you have your component database with the failure mode distribution and each component, lambda, and that goes into your FMEDA. What is produced from the FMEDA, as we saw in the earlier slide, you have your product failure rate, your product failure modes, and even your diagnostic coverage. And here at exida, we have looked at over 200 billion operating hours of field failure data from process industry to calibrate our database. In those 200 billion operating hours, we look at manufacturer field return data studies, the industry database, and end user field failure studies. And if you notice, all those were each of the estimation techniques. So now, which is probably why you're here, how do each of these methods of failure data compare? So the first example I want to take a look at is pressure transmitters. Once again, this is the same page I showed you earlier. This is a copy of the ARETA book. And as you can see, for 32 units that were investigated, we have a failure rate of 420 fits. We looked at 35 different pressure transmitters from FMEDA results and compared them with industry data from ARETA and end user field failure data from Dow. And as you can see, each of those blue diamonds are different FMEDA results. We also have graphed the exida FMEDA average, the Dow field data point, and the ARETA field data mean. So overall, the exida FMEDA results are very close or somewhat pessimistic. So they have a slightly higher failure rate, which is good for the type of failure rate you want from a FMEDA. You don't want it to be lower, and in real life you find that your failure rates are higher than what was predicted. You want to be slightly pessimistic so that you do not put your customers in a dangerous situation. The next example I want to look at is the solenoid control valve. So ARETA data provides a total number given on population. Once again, this example shows 4,718 units, and the total mean failure rate is 760 fits. So the comparison of the solenoid control valve, as you can see, we have different types of FMEDAs. You have the more simplistic type of solenoids and the more complex type of solenoids. So we put examples of a FMEDA poppet solenoid, 2 of those, a spool solenoid, and we have 3 different examples of those from FMEDAs. We have the Dow field data mean, we have the ARETA mean, you have the exida FMEDA average, and then we also have the manufacturer's warranty data and and certain certifying data. So it kind of makes you aware that you don't necessarily get all of your returns back, and sometimes you classify it as systematic when it should be random. Now I want to show you a comparison of actuator data. Once again, we have the Dow plant study. You have the exida. Once again, we have different types of FMEDAs for rack and pinion. Spring return. You have your just piston spring return. You have your diaphragm air to open, your squash yoke, the average, and manufacturer data, and an unknown method. We're going to graph this once again because I'm a visual person. I like to see what these numbers mean instead of just numbers where I have to figure it out. Once again, you have your different FMEDAs. You have your exida FMEDA average, the Dow field data mean number, and then manufacturer warranty data, which is dangerously low, as you can see. You might take a note here that the ARETA data is missing from this example. And the way that the ARETA book is shown, they don't have actuators broken out as just an actuator. They will have a solenoid actuator and valve combination. So we could not use the ARETA data to do a comparison of just an actuator. But we can match our data and build it up to match the ARETA data. So we're going to look at the valve actuator solenoid combo from ARETA. As you can see that there were 58 units, and the total mean failure rate for this example is 3,440 fits. And showing you the comparison, we have different valve actuator solenoid FMEDAs put together. Each red triangle is a FMEDA that we looked at. We have our exida mean and our exida generic number along with the ARETA number. And one reason the ARETA number is higher than the exida numbers, ARETA also has monitoring devices included, and those failures weren't necessarily taken out. And exida, we do not have data on monitoring devices since we do not consider it a safety application. So ARETA will be a little bit higher on this comparison. Once again, we're going to look at IR flame detectors. We have a bunch of different FMEDAs, the exida mean, the exida generic, and the ARETA. So we're all, once again, in the same ballpark. So we're going to now look at what is the difference between the two ARETA books. You have the Topside and the Subsea. So how does exida account for the differences between the different situations, being Topside or Subsea? Well, once again, I pull up the exida profile, and as you can see, we have a offshore and a subsea profile, so either profile 4 or profile 5, which have different failure rates per the different profile. So now, why are there differences? Well, there's the maintenance capabilities. Each company has different timelines and priorities when it comes to maintenance. You also have equipment boundaries of the assemblies. As we said, the valve actuators, solenoids, piping is also included in the ARETA data, is included within a defined boundary of a subsystem. And exida does it per device. So you would have a failure rate for your valve, failure rate of actuator, failure rate of solenoid, and so on. So when people think they're comparing apples to apples, a valve of ARETA and a valve of exida, it shows up that they aren't. Once again, the ARETA has a whole subsystem or system defined within a boundary. Now we take a look at why realistic data is actually important. Who cares? We're going to go back to the detailed life cycle in the design phase. So as we talked about earlier, you need realistic failure rate or failure data for mechanical components, because that failure rate from the manufacturer's safety manual and the database goes straight into safety calculations to find if the spill is achieved and the risk reduction factor is achieved. So if you do not have realistic failure data, you might think that you're a still 2 or a still 3, when in fact you're not. And that could put lives in danger. So we're going to look at all of the different methods we talked about today. The manufacturer field return data study, the industry databases, the end user failure data studies, the B10 cycle test method, and the calibrated FMEDA. And what is appropriate and what is not appropriate for safety applications or a static application. So as we learned from today, manufacturer field return data studies, you cannot just rely on that number, since you do not know what percentage of actual field failures are returned. And you cannot use the B10 number, since you are using an application for constant dynamic operation with a static application. But industry database information, end user field failure data studies, and calibrated FMEDAs are great failure data information. So what do you do if you see data that seems unrealistic? And the first thing I say is always question it. It is your ethical responsibility as an engineer. That was what you were taught. Always, always question it. And to do this, you can do a simple sanity check calculation. If it's not supposed to fail once, but every X number of hours, that leads to many X number of years without a failure. Does that make sense? Is this what you see in real life? Say that number is, oh, we're not going to fail until 1,000 years. That's funny, because since I've worked here, we've seen a failure. That doesn't quite make sense. So just do simple calculations and sanity check your calculations before you use them in for SIL applications. Always compare it to actual field failure data or generic failure rate data. That's an easy sanity check once again. And go back to the source of the data and try to determine what method was used to define these failure rates. Right now, we will have a little time for questions. If you have any questions, go ahead and let me know. And while I'm waiting for some questions to come in, you can always go to our website for more information. We have free web seminars, this webinar that you know of. And we have our past webinars not only on the exida website, but our YouTube channel. We have a bunch of white papers. I just published a new white paper on our website, so that's always a place to get more free information. And the Safety Automation Element List, the SAEL, that's also a link on the exida website. You can see different devices that meet SIL 1, SIL 2, SIL 3, whatever you're looking for your different applications. You can find more information there. And then, of course, we have a bunch of books from that we've published that you can look on isa.org or exida.com. And if you have questions later on, please feel free to email me at lstewart@exida.com if you think of questions later on, and I will answer them as soon as I can. We are pretty busy right now, but we can always carve out some time as soon as possible to answer some questions. A question that I just received is, when calibrating the failure rate, are there any halt methods, such as are these equations being considered for a more qualitative approach? It depends which method that you're talking about. I can speak from the FMEDA method, and we do both quantitative and qualitative approach in calibrating. We have a huge database that we look at different failure rates, and we always are calibrating our failure rates to make sure. We have over 20 years in that database that we have been mostly quantitatively calibrating. The next question is, have Exida's engineers analyzed the deluge valve and alarm valve with FMEDA? Actually, I have to look into that. I know that we've looked at alarm valves. I'm not sure if we've looked at deluge valves before. I know that they are in the ARETA book because I actually just finished reading it cover to cover. But let me take a look. We can always look on the SAEL on our website, and we can understand more from that. The next question is, how much B10 data is used in industry, used today in the industry? That I do not know. We know of companies that are using it. We know of companies that give the failure rates out as B10 data. We always say, if it's not machinery, do not use it. If it's a machinery application, great. You can use the B10 data all day long with no problem. It's a constant dynamic application. But we always say, if there's any time a static application, do not use the B10 data. We've been preaching this for many years now and trying to get a lot of people out of the habit of using the B10 data. But unfortunately, some people still are, and we see that as a dangerous approach, which could cause extreme damage to both humans, their lives, injury. It could cause damage to the environment. There's a lot of negative effects of using the B10 data now. The next question I have, for new products, how do you calculate the mechanical failure rates? We go through the FMEDA process. We break it down per the bill of material to each bolt, nut, screw, anything involved in the bill of material, and we have the calibrated failure rate for each of those components. And we look, would this screw, what happens if this screw breaks? Would it be a safe failure, a dangerous failure, or no effect? And we add up all of the failure rates along with if a diagnostic would show the problem before the problem became dangerous. And that's how we calculate the mechanical failure rates for any new product. And we actually go through that with all products that Exida certifies. The next question is there a new method being developed to access failure rate using big data? I'm not quite sure what you mean by that, by big data. The method that we use is we have our database, and it's accessible through our program Excellentia, that you can always look at all of the failure rates. We also publish our SERH books that have all of the failure rates, and our failure rates are always published on our certificates. So if you go on the SAEL, our database is constantly growing. And we continually add more information and more hours and more types of products. So we are continually growing. I think that's what you meant. I hope that I answered that question for you. At this point, I'm going to go ahead and log off. And if you have any other questions, please feel free to email me. And know that later this week you will be receiving a copy of the PowerPoint. So you will be getting an email with that. I hope you all enjoyed and learned something from this webinar, and hope you have a wonderful day.